Okay, so thank you for the invitation. I will talk about PN precision. And specifically, I will talk about the effort to complete the 5 PN precision for generic compact binaries, namely for binaries that might consist of black holes or neutron stars as components. And the challenge, my challenge is to complete these computations for components which are spinning. So let's just recall the context of the ingredients that go into the theory of gravitational wave templates. In particular, the two important theories that are employed here are post-Newtonian theory, which is valid for some regime of the gravitational wave event, and perturbation theory, which is valid to the other, for the other. And many years ago, Alessandro Bonanno and Thibaut Damour had the ingenuity to have the idea to connect these two regimes, which are controlled analytically. Basically, at the time when numerical relativity was not able to treat strong gravity. And the reason I dwell on this point is because it seems that this idea keeps serving us and giving rise to a lot of progress in this recent year. Specifically, we have a very high demand to have a high PN accuracy. And if there is a gravitational wave expert in the audience who want to correct me, to the best of my knowledge, even now, ad hoc parameters are plugged in to account for the lack of full knowledge of 6PN order, of all 6PN order corrections. And even corrections at 5PN already account for discrepancy between theory to numerical simulations, which are used to gauge the gravitational wave templates up to 10%. So I'm saying that to say that corrections which are as high as 5PN and 6PN are currently used ad hoc, and they make a difference. And in general, just to remind the notation that an NPN corrections mean a V to the power of N correction, when by V I mean the orbital velocity of the typical orbital velocity of the binary, which is a non-relativistic. I show here a table of the state of the art in post-Newtonian gravity, more or less giving you an impression of the sectors that have been approached. And this table shows non-spinning corrections and corrections which are linear in the spin, quadratic in the spin, and so on and so forth. And several things should be understood in order to read this table. First of all, that every correction enters at a relative order of n plus L, where n is this parameter and L is this parameter. So essentially, in order to complete any given precision, we have to go across diagonals. And another thing is that then one should also be aware that essentially we have this correspondence that a classical S to the power of L corresponds to quantum spin L over 2. And essentially also, even before that, when we have to take into account finite size effects, it means that from this part of the table and deeper, whatever we compute would be different for black hole. There is no longer a universal object, compact object. The computations that we will compute will no longer be in general true for black holes or neutron stars, whatever they are. It will depend on the specific UV identity of the object. So that's for the state of the art. And what sets the stage is that essentially last year, 2019, marked the complete confirmation of the 4PN correction in full totality. Namely, if we go across this diagonal, all sectors were confirmed, with the exception of a quadratic-in-spin sector that was only derived via EFT. But other results have been derived by various groups. So the challenging computation of 4PN was confirmed by the last group of Fofines to run via EFT. And close to the end of the year came an important paper of Bini, Damura, and Geralico, who exactly what I was talking about in the beginning, who using this idea of using EOB type of mappings between self-force theory to post-Newtonian theory, basically suggested a new approach to obtain higher PN corrections. An approach which would be valid, though, only for corrections without spin to begin with. That was their proposal, like corrections without spin to begin with, namely for the situation where the identity of the object doesn't make a difference, so the results are correct for black holes or neutron stars. And that basically set the stage. I mean, at this point, the stage was set to start attacking the next precision frontier, which is the 4.5 PN correction and the 5 PN corrections. And at the end of 2019, also in my work, we approached already the generic correction of 4.5 PN, which is designated by this sector of next to leading order cubic-in-spin via the EFT. So this will be included in this talk. And when I'm saying generic, I mean a correction which is valid for either black holes or neutron stars. And as it turns out, 2020 was a difficult year in many respects, but so far it's been pretty good for progress in post-Newtonian gravity. In particular, in an impressive series of works, the 5 PN correction for just the sector which is non-spinning was completed by Bini, Damura, and Geralico, later with the help of Laporta and Mastrolia, although not fully confirmed yet by other methods. Then also generic corrections at the 4.5 and 5 PN with spin. I and my group and my students continue to tackle them via the EFT. So basically the sectors which are shown here and the sectors which are shown here. And then inspired by this novel approach, which was suggested by Bini, Damura, and Geralico, also the Potsdam crew extended this idea to the linear, to corrections which are linear in the individual spins, where still the identity of the specific object doesn't make a difference. And they approached also the 4.5 and the 5 PN corrections with spin. So let's talk a little bit about how these corrections work out. I will dwell this time more about on higher spin sectors. So to begin with, we define the generalized velocities, and we talk about the effective action of a spinning particle. And this was done many decades ago by very, very good works, which analyze this for the case of flat space-time and curved space-time. And essentially, EFT people, we adopted this formulation, basically just with the observation that we want to consider the spin itself as a classical source on our word line formulation, and with the prudence to remember to consider the spin as an independent particle degree of freedom, which was crucial all along the way. And also this specific form, which was known, as I said, for decades, implicitly assumes a certain natural gauge, let's say, and a preferable gauge, which was first introduced by Tulchev in 1959, who was the first one who got the first post-Newtonian correction. And that was the starting point for the further progress which we did with the higher spin. So then in work which was done with Jan Steinhoff, we wrote what would be the non-minimal coupling extension of this simple spinning particle action. And we wrote an infinite series, namely like all the couplings, which would be linear in curvature to all orders in spin, essentially introducing an infinite set of spin-induced Wilson coefficients. And Tanya previously told us a little bit about recent studies about these Wilson coefficients, or as she calls them, like the love numbers or rotational love numbers. And I should highlight that while there has been many conjectures about these numbers for the case of Schwarzschild black hole, the case of a spinning black hole was much less studied, and there is, in general, much less knowledge of what are these coefficients without any approximations made, namely on the slow rotation of the object, so to the best of my knowledge, for example, like this very recent work of Chia from 2020 was the first one who made the statement regarding an exact care. And even on that, I had the impression that there is still a debate. So just to kind of let you know what is the state of affairs, in that although we write an effective action, there are still black boxes here which should go through a matching process, a full study, which would be a matching of these coefficients. So these are still not fully known. Extracting from this series in order to now attack this to attack the next precision frontier, which is the 5PN order. Then three terms are relevant, which are linear in the curvature. So the quadrupole coupling, the octupole coupling, and the hexadecapole coupling. Essentially, the spin vectors here play the role of a similar role to like SU2 spinors, which are in direct product, if formulated in spinor helicity formalism, for example, which was recently made for massive spins. So it's essentially very similar. And indeed, that was all that was needed when the previous challenge was to conquer the 4PN order. So in a work which was published some years ago already, once we formulated these couplings, cubic-in-spin and quartic-in-spin, we were pretty easily able to derive the leading order corrections, cubic and quartic, which contribute to which allowed us to complete the 4PN corrections in spin with spins. Let me just state the curious fact, which I didn't highlight previously, is that at this there were still ongoing studies of what are the 4PN corrections without spin when the corrections with spin were already finalized. So just to say that, although there is still this one sector which is unconfirmed, I would say that the situation with the spin sectors is pretty much under control. So going back to this correction, which was introduced some years ago and allowed us to complete the 4PN accuracy with spins. Then, as I said, recently in the end of 2019, I set the goal to attack the next precision frontier. And the point here is that the loop computational challenge here is not the issue in the sectors of higher spin. In fact, even just the derivation of the Feynman rules, which you could see from the form of the couplings here. I mean, even just the derivation of the Feynman rules from this term compared to the Feynman rules which are derived from the simple non-minimal coupling terms is so much more intricate and subtle And in fact, I would claim that the effort and the carefulness that is needed in order to make this derivation correct is more or less equivalent to the effort that one should put in evaluating all the diagrams, which are quite a lot, something like 50 diagrams. So that's one thing I wanted to highlight, is that the derivation of the next to leading order Feynman rules becomes quite intricate and subtle. And again, we basically get the whole sector by taking into account all possible interactions between different higher multiples located on the one of the two word lines. And so essentially, here there is an additional complexity, and that is that from the fact that now we are in next to leading order, no longer in leading order, what we call the canonical spin variables, they are no longer trivially the same as the covariant spin variables, and therefore also one has to make a non-trivial switch between the covariant to the canonical variables, which are the ones that we've ultimately used to present the result, and they are the ones that make sense also physically. And so because we have to make this switch in the gauge, in our choice of spin variables, things which originally appear as a linear coupling in spin, in fact, turn out to contribute to cubic-in-spin couplings, which are located on a word line. So in this transition, in fact, now there are created some kind of new composite octopole couplings, which are not the same as the elementary couplings that I showed you here, which were presented directly with the spin vector, which is defined with the covariant spin. So that's the complexity that there is still at the level of 4.5 pn. However, when one sets the ambitious goal to conquer the 5 pn precision frontier, now there is a qualitative difference that also is relevant for the non-spinning case, and that is in principle that now we have quadratic in curvature corrections that enter. And notice that this hierarchy that we saw previously, which was pretty natural, that when we went up with the order of spins, then the corrections that are linear in the curvature, they came in gradually increasing PN orders. This is no longer the case when we talk about couplings to quadratic in curvature corrections, because, for example, if we take the even in spin sectors, namely the ones where there is no spin, the one where we are quadratic in spin, and the one which is quartic in spin, all of them contain corrections which are relevant at 5, which enter all at the same order at 5 pn order. So there is no longer this hierarchy, as I said, which is kind of somehow linear as we had before. So specifically, I'm noting that because these corrections, of course, are relevant to all the sectors that I mentioned that were attacked in my work, specifically the quartic-in-spin, the next to leading order quartic-in-spin, which, as you can see here, since it's quadratic in Riemann, it means that we will have a quadratic graviton coupling. In leading order, it will give rise to a two graviton coupling. And also for the quadratic, just the simpler quadratic in spin correction, we'll also have to take into account such a two graviton correction already. So, and if I told you that people approaching the study of rotational log numbers I still believe it's still very much in its infancy. For sure, these new coefficients, to the best of my knowledge, really haven't been studied even in traditional gravity studies so far. So to the best of my knowledge, nothing is known about these coefficients yet.
You have 5 minutes left.
Sorry?
You have 5 minutes.
5 minutes. So just to give credit to whom credit is due is that in principle, so all the type of corrections that come after the first line were already described by Bini, Damour, and Fay in the non-spinning case, were already treated in this paper. So in order to do the Quartic-in-Spin sector, we have like similar kind of combinations like the ones that we saw in the Cubic-in-Spin sector. And though the elementary graphs, namely the graphs which contain elementary couplings, those which are given in directly in terms of the covariant spin variables, are fewer and simpler, those which arise from the transition from the covariant spin variables to the canonical spin variables give rise to more options of such composite couplings. That's one thing. And the other thing is what I just showed you now is that now when we are in 5p, Quartic-in-Spin sector is already at 5p order. So now we also have to take into account relevant operators which are quadratic in the curvature that are also contributing. So from the expansion that I showed you earlier, there are two terms, and it turns out that that in fact only the electric operator enters at the leading 5p order at the order of the sector that is considered. And as I said, we have a new unstudied Wilson coefficient which is connected with it. And as I noted, now we have like more kind of composite kind of couplings, namely a dipole, a quadrupole composed on a dipole, or an octapole which is composed on a dipole, also contributing to this sector. And then finally, I will really quickly just say that then the challenge in the higher loop sectors was completely different. Like once one does the extension of the action, the challenge in the higher loop sectors was completely different, and basically boiled down to really classifying the structure of the topologies really well and understanding which topologies mean which type of integration. And basically, in terms of technology, the big leap was that if previously, when only two loop level with spins was tackled, it was good enough to let Mathematica create IBP reduction relations by hand, although it's Mathematica, but still, I mean, in a way which is similar to the way we produce them by hand. The big leap in terms of technology was to just make an algorithmic, introduce algorithmic IBP to the E of T of PNG code, which is the public code that computes all these type of corrections within the effective field theory of spinning gravitating objects. So I don't know how much time I have, so I'll jump to the conclusions. Just say that basically the two important observations about classifying the bottom line of classifying the topologies is pretty simple, essentially. And we didn't see it, although, I mean, three loop level was already tackled before. I mean, for example, without spin, we didn't see this type of classification appearing before. And it did inform us about what comes out of the computation. So essentially, two things had to be noticed. First of all, is that one can identify at every order of topologies some kind of basis integrals. So at the two loop level, for example, we have two such base terms. In three loop level, we have three terms, but if you think that for every loop level, it's the same number, so it doesn't hold for beyond three loop level. So in principle, we made this definition of saying that the topology is rank R according to the number of basic.
Hi, Michèle, we're running out of time. So
yeah,
if you don't mind.
I'm just about to finish.
Thank you.
Yeah. Basically, just saying that a rank R topology is just saying how much basic integrals are needed in order to get the integral that represents this topology. So that was one observation. And the second observation is just to define what is an N-loop topology in what we call the Worldline picture. And using this definition, we were able to say what are the highest loop topologies within all the group of 32 topologies in this sector. And basically then we knew that all the special features and more complicated features, we could see that they come only from what we defined as this 3-loop topology. So this was essentially what had to be tackled when going to the higher loop sectors. So I will conclude briefly by saying that we have achieved the real world scalability, because essentially the only thing which was needed in order to know that we can handle the next to leading order sectors was to know that we can break down these 3 rank topologies, which are the hardest to evaluate. So this is already there, and we continually develop the public EFT of PNG code, so there's no problem with this aspect. We have a self-contained framework in the sense that by construction, we are able to directly derive useful and physical quantities. And by that, I mean useful, for example, Hamiltonian, which is useful for LIGO templates, but is not a physical quantity. Whereas we can also derive physical observables, for example, like binding energy. And we are also directly able to do self-consistency checks. And in that respect, there is an important work in progress that is done by the wonderful student Roger Morales with me. And finally, the complete precision frontier with spins at 4.5 and 5 PN is really within reach, and really it's underway to be completed. And I will just note that also there are yet more lessons to be learned from finalizing and concluding what would be the outcome of the nonlinear higher spin interactions that were evaluated. So I'll finish with that, and thank you very much.
Let's thank Michèle for her talk. And we're out of time, but since we have an hour break now, maybe people want to stay and ask questions. If you want to raise your hand or just unmute yourselves if you want to stay here for longer. There's a question by Gabriel Luz Almeida.
Hi, Michèle. Hello. Thanks for the nice talk. What I would like to know is whether or not you have considered hereditary effects like tail effects in these computations.
They are not relevant yet at this level because we are talking about corrections with spin. And I mean, there are tail effects which are relevant. There are hereditary effects which are relevant for 5PN, but those do not involve spin in particular. And they were computed actually also at the end of last year by Fofa and Sturani. But the tail effects which are associated with spins, they come actually at higher orders.
Okay, thank you.
And there's also a question by Irvin Martinez.
Hi, Michèle. I would like to ask you, what's the analog of the effective one body in effective field theory? I mean, it has been used, effective one body, to extract gravitational waveforms, but how do we actually extract the waveforms with effective field theories?
Effective field theory, first of all, the effective of effective one body and effective field theory is a different effective. So they are not the same. Effective field theory that I'm using, you can formulate any effective field theory that you want as long as you work in a certain approximation. I work in the approximation of non-relativistic velocities. So I derive results for post-Newtonian theory, which are used as input for EOB, which, as I showed, maps PN results to self-force theory results. So that's the connection. There's no special connection between EFT and EOB in the sense that every method that you use to produce PN theory results is as good to inform the gravitational wave templates. One thing that I should say, by the way, that I forgot to say when I was talking about the novel approach that was introduced by Thibault and was used by them and also by the Potsdam crew to derive recent results at 5 PN and 4.5 PN, is that obviously it's very nice that there is a new way to derive post-Newtonian results, but this comes on the basis of having already results from self-force theory. So it's not an independent theory by itself. It's not an independent theoretical formulation by itself. And so if in the past, pure post-Newtonian theoretical formulations, we were able to cross-check them by comparing against self-force theory. Here, self-force theory is used as an input. So, which means that that for sure there should be other formulations for PN theory to contrast in order to cross-check such results. So I answered more than what you asked, but hopefully I informed you in some way.
Thanks.